Kia ora, and here's another really old question from 2009. So this is from the integration paper, and it's a skill that actually isn't required anymore, except that it could still pop up. The only thing is that now if it came up, you would be given the formula. So this is the question here, and so I'm going to teach you how to do these things called volumes of solids of revolution. If you're in the A-level class, then we've already done this, but this is just a slightly different example. So we're given a region here, and it's bounded by some different lines. So the first of them is it's bounded by the curve y equals log of x, right? And then we've got a vertical line at x equals 1, the x-axis, and y equals 2. And we have to calculate the volume of the solid generated if it's rotated about the line x equals -1. So the x equals -1 is what makes this question slightly harder than usual. What we've got to do is imagine that we're making a nice piece of, I don't know, a pottery vase of some kind. Right? So we're going to take that two-dimensional cross-section, and I want you to imagine that you're swiveling that all around. Right? So you're turning that around, and you're going to end up with, oh, this is a big mess now, right? But you're going to end up with a shape that looks like this. So that's kind of hard to see how I've drawn it. I'm going to do the easiest possible example first, and we'll look at how we could work out a formula for these things. So suppose that instead we've got a graph like this, and we've got the line y equals x. And I want to rotate that line from, say, 0 out to 5 around this axis. So I'm taking this, and I'm going to form a three-dimensional shape, and it will look like a cone, right? And this is how you can derive lots of the formulae that we use all the time. If you think about what you're doing, you're going to be taking the height of that curve and making a disc, right? So you can picture a circle here. Well, the circle on the outside would have an area of pi r squared, right, which would be pi times 25. And you can find the volume by adding up an infinite number of very, very thin disks. And that means that in general, when we want to find the volume of solid of revolution, we do it like this. So here we'd go 5, the integral from 5 to 0 of pi r squared. So r is changing for all of those disks, but it's given by the height of the function. So that's how we do a volume of solid revolution problem. There are a couple of little tricky things in our question here, though, and here's the first one. Let's get rid of all the muck. The first thing to notice is that we are not rotating around the x-axis, we're rotating around the y-axis. So well, my formula is going to be something like this. Instead of integrating with respect to x, I'm swiveling this way, so I want to have pi r squared, but that's going to equal pi times f of y squared integrated with respect to y. So my y limits here are going to be 0 and 2. So that's not too bad. We're going to need to rewrite this to make x the subject. But what makes this harder is that I'm not rotating around the y-axis. I'm rotating around this line here. This question would be much easier if we could shift everything over so that we were rotating around the y-axis. And that's what I'm going to do now. So I'm going to take my line here and I'm going to shift it to the right 1 unit. So moving down here, the area that we're trying to find is exactly the same as if I take that curve and I shift it over 1 unit to the right. Very badly drawn. Hope no one's watching, right? So to shift something to the right with any function, I'm going to change it to be x minus a. So here it's going to be y equals the natural log of x minus 1. And now I'm going to be doing a standard volumes of solids problem where I'm rotating around this axis and I've got these limits here. So these limits are going to be given by 0 and 2. So what we need to do is to rewrite this with x being the subject. So e to the power of y is equal to x minus 1. X is equal to e to the power of y plus 1. Now we're ready to do some integration. So the volume will be the integral from 2 to 0 of pi f of y squared dy. So f of y squared is equal to e to the y plus 1 squared, which equals e to the 2y plus 2e to the y plus 1. So my volume is equal to pi times this. So when I integrate that, we've done all the hard part now. We've got pi times 1/2 e to the 2y plus 2e to the y plus y, evaluated at those limits. So you can chuck that in your calculator now, or you can do it by hand like I did. So we get 1/2 e to the 4 plus 2e squared plus 2 minus 1/2 plus 2 plus 0. So that's substituting in the 0. Just be careful there, you don't get 0 for a couple of those terms. And when you chuck all that into your calculator, you get pi times 41.577, which works out to give us 130.6186 units cubed. Let's see what we had for units. Yeah, just units cubed. So I'm going to round that to that. So there you go. So a few things to note there is that now you would be given a formula for volumes of solids of revolution, and you probably, I don't think, would get a question in level 3 where you had to do that with rotating around the y-axis, but it's conceptually not that difficult if you've got the hang of rotating around the x-axis easily. And the nice thing that I really liked about this question is that you had to do a translation of that graph 1 unit over. So I think all of those skills are really good ones to go over. You probably won't get them all combined into one question like that next week though. Thanks for watching. Let me know if there are any more questions that you want done.